focused at monsoon prediction. So so this work is done, whatever I am showing here is all these works are done in collaboration with Professor Hari Prasad Kodamana, who is faculty in chemical engineering and also jointly with the School of AI, and our PhD students actually. So I'm sure that Rajivan sir has yesterday talked about monsoon prediction, its details. So I'm not going into the technical details of that, but just briefly, in one slide, I talk about the logic behind different scales of prediction. Yeah. Okay. Yeah, I think it is coming. Oops.
Now this is coming, that's all.
That should be okay. Yeah. Okay. So, yeah. So, basically, the monsoon prediction has a long history. I have read that the first official forecast was made in the year 1886 by, if I am not mistaken, by Blandford. And ever since, I mean, every year the monsoon seasonal forecast was being issued. But we know that the predictability of atmosphere is about 7 to 10 days, and in the tropical region it is even less. So because atmosphere is chaotic, this was proved by Lawrence way back in 1960s. And why do we actually do the seasonal prediction of monsoon or subseasonal prediction of monsoon when the predictability of the atmosphere itself is much shorter? So, so there is something that we need to know here. So within the atmosphere itself, there can be some recurrent oscillations. So these inherent oscillations can be used for prediction. I mean, that gives us a longer window of predictability. And as in the case of monsoon, it is influenced by the external drivers such as sea surface temperature. So these are very slowly evolving phenomena such as El Nino Southern Oscillation. So when it is controlled by such low frequency dynamics, then that again gives us another window for longer predictability. That is the seasonal predictability. So that is the logic behind why we are even attempting longer range predictability than the theoretical predictability limit of the atmosphere. So yeah, this is a nice schematic I have taken from this work shown here. So where they have actually nicely represented all the large scale phenomena that has an influence of monsoon, on monsoon, such as El Nino Southern Oscillation, Indian Ocean Dipole, North Atlantic Oscillation, and also the snow depth and soil moisture. These are all giving us predictability in the longer term. And within the monsoon, there is monsoon intra-seasonal oscillation. So when I say this gives longer predictability, it is again not a linear relationship. When El Nino, for example, El Nino and Indian summer monsoon, it is not a linear relationship. We all know that if there is an El Nino, then mostly people say that it is going to be a drought year. The monsoon is going to be less than normal. But here you can see, so this is an index for El Nino. So positive means El Nino, negative means La Nina. So you can see that most of the monsoon droughts, so this is y-axis is Indian summer monsoon rainfall anomaly, all India average rainfall anomaly. So most of the monsoon droughts were in the El Nino year, so positive Nino index. But you can see there are some normal monsoon rainfall also happened in during El Nino years. For example, here this is a very strange thing that happened in 1997. We got the largest or strongest El Nino ever in the recorded history, and that turned out to be a normal monsoon year. So everyone except IMD predicted a drought year, but IMD predicted a normal monsoon year. It turned out to be correct, but I was told that the IMD model always predict normal monsoon at that time, the statistical model, and in 2002, I think, there was a drought monsoon, and at that time it was realized that this model always predicts a normal monsoon. So yes, so but this is, yeah. So these are, so there is a high level of non-linearity here. The predictors, I mean the relationship of Indian summer monsoon with the predictors like El Nino is not actually linear. So that poses a great challenge here. So so yeah. Yeah. So the El Nino itself is it has a longer predictability. So even using dynamical models, we get like 6 months of predictability for El Nino. So this was one of the biggest success of climate science actually in the recent history. So in 1980s, we were able to successfully predict a forthcoming El Nino about 6 months in advance using a numerical prediction model. It is because of the slowly evolving dynamics of the ocean dynamics of El Nino. So so there is something called a spring predictability barrier. So which means that before the spring season, if you start, if you try to predict El Nino, your chances of getting your forecast is actually not that good. So after the spring season, you can predict it, your predictability is higher. So, but one of the recent successes of the machine learning models is that many models were able to show that the spring predictability barrier can be broken by the deep learning models. So there was a paper that was published in Nature where they used a convolutional neural network to predict El Nino about 18 months in advance. And following that, we have done, I mean, this is a work we did with a BTech student, Mayuna Gupta, and she used a convolutional long short-term memory model to predict the Nino 3.4 index, which is the it is the sea surface temperature. Yes, only data is given as the input, and we were able to predict the El Nino 12 months in advance. So our the forecasts were initiated in January, monthly sea surface temperature basically. So you can see that three cases of El Ninos are shown here. We compared that with operational, dynamical, and statistical models. So all of these are archived by Columbia University, so where you can access all the El Nino forecasts, even real-time forecasts you can see. So we compared their January initialization of dynamical models and statistical models with our convolutional LSTM forecast, and we got reasonably good. So this red curve actually shows our prediction, and this blue is the blue curve is actually the observed evolution of Nino 3.4 SST. So green is a average of the statistical model predictions, and black is average of the dynamical model predictions, and we have also shown the standard deviation among the predictions of these models. So this shows that the ML models can actually do good when in the case of a slowly evolving system. So then we actually focused on the monsoon intra-seasonal oscillations. So within the 4 months of monsoon, if you look at the daily rainfall variability, this is taken from IMD. These figures are taken from IMD website. So this is actually for this year. So daily rainfall, you can see there is a fluctuation. So, and this red curve is actually the long-term climatology of daily rainfall, smooth curve. So if you subtract this long-term climatology from daily variation, you will get this. So all India level data, yes, all India day rainfall average. Okay, so you can see that there are some negative values, which means the below normal. I mean, the rainfall is less during these spells. This is a break spell. This is for actually the last year. So because this year monsoon is not yet complete, it's still ongoing. So I took last year's data. So you can see that there are spells of active and break cycles. So this is basically part of the intra-seasonal oscillation. So since this is another oscillatory system, we thought that, okay, this can also be learned by the deep learning model and we can predict it. So, so this is a spatial evolution of these rainfall anomalies. So from a break phase to an active phase. So these blues show negative anomalies, which means a break phase, and the reds show the positive anomalies of rainfall, which is when it comes over the continental India, it is active phase. We get a lot of rainfall. So so what we do is that we take the three-dimensional data, latitude, longitude, time data, and we apply a principal component analysis. So this was already done by previous works, previous studies. So we know that the first two principal component time series actually represent this evolution of this intra-seasonal oscillation. So this can be nicely represented in a phase space diagram. So from clockwise here, you can actually track the movement of intra-seasonal oscillation. From each subquadrant is identified with the location. So you can actually say that at which location is the cloud band is actually located now from this. So now there is since we are trying to actually start with a very simple prediction, we are trying to predict these indices rather than the rainfall directly, because I will show you why. I mean, it is not easy to predict rainfall. I will show you, we did that also. But these indices, we call it Monsoon intra-seasonal indices, so MESO 1 and MESO 2. Using these two indices, we can actually represent the oscillation of the intra-seasonal oscillation of monsoon. So, yes, so here we did not actually took area average or anything. This is a principal component. So you took a larger area, so did a PC analysis, you get a principal component time series. So, so it is actually, it represents, I mean, all this domain. Yeah. Yes, yes, yeah, yes. So if you go to smaller scales, you will have a very chaotic system. You do not have this smooth oscillation at a very small location. So for the time being, we are actually looking at a large. Yes. Yeah. Different, I mean, I'm talking about in terms of the temporal oscillations. Spatially, from place to place, it can vary. For example, if you look at the Western Ghats, the characteristics of that oscillation may be different from that of Central India. So, yes. So, this is, I mean, we tried to model this with two different standalone machine learning models. I mean, one is a simple LSTM model, and another is a transformer model. So we trained, we used, since we also wanted to cover the ocean. So this is starting, this convective band starts from the equatorial Indian Ocean and moves northwards. So to completely, in order to completely represent that oscillation, starting from equatorial Indian Ocean to all the way to the continental India, so you need to have that data coverage. So right now, we have a global satellite based rainfall observation. It is called a tropical rainfall measuring mission. It lasted, I think, it lasted from 98 to 2016, and it was followed by something what is called Global Precipitation Mission, GPM. So we combined these two data sets, and it gives you like 25, 26 years of satellite-based rainfall observations. So we used these rainfall observations to extract the MESO indices. We applied PC analysis on that and got MESO 1 and MESO 2 indices, and used 20 years of data to train the model, and then 5 years we used for validation. So 20% of training data is kept for testing. So then this is the comparison of our two deep learning models, LSTM, transformer, and this is observation. This black cover is observation. So you can see that the transformer is closely following the observation. And we have also compared this with the two global, two numerical weather prediction models, NSEP and UKMO. So they are also, their subseasonal to seasonal forecasting initiated on 1st June is taken. And these are all, 10-day lead predictions are taken here to compare. So what we found is that at 10-day lead, these two ML models have good skill in predicting these indices, MESO 1 and MESO 2 indices. So if you see the phase space diagram, this is the observed evolution of intra-seasonal oscillation for the year 2022. This is the transformer, not bad, and this is the LSTM, and this is NSEP NWP model. So we did not try that. Yeah, yes, yes. Okay. So yes, this again shows the deep learning models have some skill in this. But this is not a fair comparison between the NWP models and the deep learning models, because here I have used the precipitation forecasted by the NSAP or UKMO models and extracted the meso from the forecasted precipitation, and here I predicted meso 1 and meso 2 directly using a machine learning model and compared these two. So direct prediction of rainfall is actually challenging. I will show you that in a moment. But when we look, yes, past 64 days of data is given, and next 10 days forecast is made. 21 days forecast is made, but what I have shown is actually the 10-day lead forecast. Yes, that is for training. So, but for initiating, before initiating each forecast, you give 64 days of past data and do it. It is a very index, right? It's a very small data. It's not deep. So, yeah. One thing that we have seen is that in the transformer model, the error growth is actually very less. So with time, so my colleagues who are working in ML, they were saying that okay, the transformer model is basically used for large language modeling LLMs, and they are good in predicting long sentences. So this might be, I mean, this is an analog to meteorological predictions here. So they are already known for predicting long sentences. So here, so that means they have some long prediction skills, long range prediction skills.
You decoded the transformer, or you used some autoformer, reformer, those kinds of codes? Or?
No, I frankly speaking, I do not know that much. I mean, technical details of that. I mean, that part was taken care of by my colleague. So this is an encoder decoder. This is there. So.
Because nowadays there's a lot of interest in time series modeling
Yes.
using transformers and
Yes.
these various.
Yes.
The one which is best running is the patch TST model.
Okay. Okay, that we didn't use.
Is patch TST better than others?
So here is our prediction of rainfall anomalies, spatial prediction of rainfall anomalies itself. So you can see this is an observation. I mean, this is one random date is taken, and this is the observation, and this is 1 day ahead prediction, not 10, 1 day ahead prediction. You can see that this positive anomaly is, I mean, there is pattern-wise, it is something it is capturing, but its strength is very, very less. So the amplitude is highly underestimated. So this is a problem when we try to do the rainfall forecast. So I will show you some of the models that Dr. Amal Jyoti discussed also, the global models, global machine learning models. Many of, I mean, they are also having issues in rainfall prediction. So now, I mean, so here, when we tried, I mean, this is again work in progress only. We tried to improve, and we look deeper into this. So rainfall, spatial evolution of rainfall prediction is really challenging. So then we tried a seasonal forecast of monsoon rainfall using neural GCM. Not just rainfall, actually this is a seasonal forecast using neural GCM. Neural GCM is probably the most recent among the global machine learning models. It is again GraphCast and neural GCMs. These are both developed by Google. And this is, unlike other ML models, this is a hybrid ML physics model. So which means it has a dynamical core, just like any other numerical weather prediction models, and physics is parameterized. Physics